Hi, welcome to part 2 of Where the Really Hard Problems Aren't, in which we were occupied with the asymmetric traveling salesman problem, which is usually given by a matrix only. Now, Cheeseman, or for short Cetal, in his original findings, filled up a bunch of these matrices with a log normal distribution with different standard deviations and a mean mu of 10 constantly. And what he found was that as the standard deviations are increasing, that the time for Little's algorithm to find the optimal route from one of these matrices decreased. So for standard deviations over 2, roughly, the computational cost to find the optimal tour was very, very low. This in itself is a very, very strong result, because really the big $1 million question in computer science is P equal to NP relies on computational costs of the most efficient algorithm for a problem available. So if for some problem over half of its instances turn out to be really, really easy, this would have been very, very significant. The problem is probably that this relies on a mistake. Now, you might have noticed that this figure from Cheeseman is rather rough. This was the whole reason why we wanted to replicate the original findings. So we did, as Cheeseman did, we used this log normal distribution with different standard deviations and a fixed average mu of 10 to fill up these matrices. Here, every dot is a matrix, and crunch them by Little's algorithm. And we found exactly the same, but similar results. Now, our axis is a little shorter than Cheeseman's over here. So these results are comparable. This would have been a succeeded replication. But then something went very, very, very wrong. Because at one instance of the runs, we forgot accidentally to do the round off. Right? So you should imagine that this log normal distribution produces a lot of floating point numbers that you put into a matrix, and then you have to round them off to integers, as Cheeseman did. But we forgot the round off, and then what happened was this. The whole phenomenon disappeared. Okay, these results are interactively available, and I made a little movie clip from what it looks like and how these results change from exactly replicated to completely different as we switch to from floating point matrices to the accompanying integer matrices or back to the original floating point matrices. Look at this. So here's the site. It's made by Gijs van Hoorn. We click 48 cities, which is a lot of data. We just click on one point and we get the accompanying matrix. Yeah, go down. There it is. This is the accompanying distance matrix. This is the instance of the asymmetric traveling salesman problem. And the dot here implies its computational cost. Here's some averages. Now let's switch to the same floating point matrices from before the round off. What happens? Boom, it's gone, the effect is gone. This is the accompanying cost matrix. You can check these numbers for yourselves. You can also download them from a different site. It's all on the paper, and the figure looks very different. Let's go back to integer, and watch this point collapse. There we go. Bang, it goes away. So really, it must be something in the round off. But what? Okay, so let's have a look. We have an explanation. So Cetal used this log normal distribution, presumably because it has produces only positive values on an open-ended scale. right? But if you fix the mean and you increase the sigma, this is what happens. So for low sigma, all the whole distribution looks a little bit like a bar, like a little bit like a softly inclining dune. But if you increase sigmas to 5, then you get a whole lot of really, really small values compared to a very few very large values, right? That's what happens when you increase sigma. So assuming that these small values accidentally got rounded off to 0, can we predict the number of zeros which we could expect for a certain sigma in an accompanying distance matrix? And the answer is yes, from the cumulative log normal distribution. You can see it here. This is the cumulative log normal distribution, and you can see the chance that some value falls below the 0.5. We just assumed 0.5 as a round off point by these different lines over here. So for sigma x2, almost 1/3 of the values would be smaller than 0.5. For sigma x5, the largest sigma in achievements results, it would be over 95% of the values. So these values all get round off to 0, is our assumption. And now this provides, and this takes a little bit of abstraction, this provides another means of explanation. So we see that from this log normal distribution, this cumulative log normal distribution, we can calculate the expected percentage of zeros to be present in the matrix of an asymmetric traveling salesman problem. But we can also measure, of course, the actual number of zeros, and those are very, very close together, which is not surprising for such a big data set, right? But here comes the abstraction, and it's a little difficult, so if you don't get it in one go, just skip it. There is a connection between the Hamiltonian cycle problem and this zero-cost tour phenomenon. And that is very old work by Komlos and Temeredi, and they predicted the chance of a graph being Hamiltonian, having such a loop in here. See, a green loop that visits all the vertices exactly once. And this chance increases with the number of edges in the graph. Now, in a similar way, and this takes some abstraction, the presence of a zero-cost tour can be predicted from the number of zeros present in the matrix. And that number, and you can find the formulas in the paper, is given in red here. So here's the expected number of zero-tour matrices, and the non-dashed line is the actual number of zero tours. And what happens if a matrix actually contains a zero tour? Well, then if you feed it to Little's algorithm, it will bang all the way down, find the shortest route possible, discard the rest of the search space, which is an enormous amount, and as a result, keep its computational costs really low. So this is what we think happened in the original paper by Cheesman, Konetsky, and Taylor. Just an overlooked zero round-off from floating point to integers, which produce a lot of zeros and dropped the computational costs. So if you're still interested, I really invite you to read our paper, which is called Where the Really Hard Problems Aren't, written by Slegers, Olij van Hoorn and me, and some acknowledgements to some people from Amsterdam and from outside of Amsterdam. And one last acknowledgement should go to this guy over here, this Ruben Ruiz. He is the editor-in-chief of Operations Research Perspectives, and is a really, really good and communicative editor-in-chief, and he really facilitated the review process and communication with the reviewers a lot. Okay, if you have any questions, if you have any comments, if you have any counter information, We could be wrong, of course. You never know. Science progresses one step forward and one step back at a time. Please drop your comments and questions in the comments box, or drop me a line on LinkedIn or Twitter or Facebook or whatever. I'd be happy to help. Thank you so much for watching. See you next time. Bye bye.